Welcome to today's lesson. Today we're going to be talking about how to identify AC current, some of its characteristics, how it's generated. We're going to describe what AC waveform looks like, and then some of the different values that we're going to use to describe AC voltage, AC current, and also how to get frequency out of generators, and talk about generation of AC current. So as a slight review, we know with DC current, basically if we have a current value in a circuit, over time, it doesn't change. So if this is our time, and let's say this is current, basically as soon as we start, we might have some ramp up, but the current stays constant throughout the circuit as long as the circuit is on. With AC, we actually have a different waveform. You can kind of see it here in this image. This is a long exposure of city lights over time, but this waveform, especially the one down at the bottom, is very close to what our AC circuit or AC current would look like. And so let's say this is 0. Instead of DC current always being positive, always flowing in one direction, we're actually going to have a current that's going to go up, come back down, and several times over however long we run our circuit. But in this, when it's positive, it's running in one direction, and then it actually switches directions and flows in the opposite. And so we'll talk about this a lot today while we're talking about AC. This is the fundamental difference. This is what it looks like. You've got constant current, and then you've got a changing current. And this change is both magnitude and direction. So not only is the current getting higher, but or changing directions, it's also getting greater and then going back down. So we'll talk a little bit about why we have AC and DC. Beyond the historical aspect of Edison versus Tesla, direct current is useful. It's very portable. It's very efficient. It's what powers your cell phones, your small handheld devices. Batteries are DC current examples. But AC current is easy to transmit over long distances. So with DC, we kind of have like a constant voltage, and we have to transmit that. And so if we were to do it over a long distance, we talked about resistance and conductors, well, eventually you're going to have a loss over a long distance with a DC voltage. With AC voltage, what we can do is actually step it really, really high, and then we still experience loss over a long distance, but that loss is very minute compared to how big our voltage is. So then when we get back, or when we get to a substation or something down the line, the loss is minimal, and we can actually step it back down and get the voltage that we still need. So you can kind of see here power lines. All the power lines that you ever see are probably going to be AC voltage. They're going to have AC current flowing through them at some really high potential. But when we talk about aircraft, it's actually also advantageous to have AC because we can have smaller motors, smaller generators. They can save us space and weight on aircraft versus a DC motor. And then there are a couple additional effects that are very useful in AC. We're going to talk about these also later. This is inductive and capacitive reactance. So a review of EMF, when we talked about how to produce an electric field, what its effects are on a conductor and such. Well, this is very important when we talk about AC generation. So when we're generating electric current, we basically have a large magnetic field, and we pass some sort of conductor through it, and we induce a current. With DC, you can't really do this because you have to basically pass some conductor through a magnetic field at a constant rate. It's not very useful. With AC, we can change the rate, change the current, and we can't just hold the conductor still for DC because then you don't have any change in current. So with this, when we talk about generators, we're going to need to use the left-hand rule to determine what our output current is. This isn't the same left-hand rule that we used when talking about producing magnetic fields, though it's a similar process. So in this case, in this image in the lower right, we can see a magnet and a conductor, and then we've got a nice graphic of the hand rule, the left-hand rule. In this case, what you're going to do is you're going to point your pointer finger in the direction of the magnetic flux, so north to south. You'll point your pointer finger towards the south pole of a magnet. Then your thumb is going to be the direction that you're moving your conductor through the magnetic field. So in this case, they have their thumb pointed up, which means they're moving that wire on the right up through the magnetic field. So in that case, our the last point of the left-hand rule is our direction of our current is given by our middle finger. And so you can kind of see it here. It's better to look at the picture because I'm mirrored, but we see that the current is flowing in the direction of our middle finger if we follow this image. So when we talk about AC generation, we're not talking about a static field, though. We have a static field, but we're not talking about a static movement. We're not just moving something straight up and down. It's a little more involved. So you can kind of see here, there's a nice demonstration of how an actual generator would work. What we do is we take our conductor, our coil of wire, whatever it is, and we sweep it through a magnetic field. So instead of, just going straight across through, let's say these are our magnetic field lines. We'll draw some arrows through them. And this is our conductor. We're not just moving it straight up and down or forward and back. In the case of AC generation, what we actually do, we'll say this is our path. So we've taken a conductor and we swept it through. So here, what we're going to do is we're going to rotate our conductor through a magnetic field. So we're going to get a path like this. What you can imagine is as you get higher and get through this, you're going to have more effect on your current. And so you can kind of see in the graph, as we move through, we kind of get this output waveform that goes up and down and up and down. And so this is how all AC generators work. We might have more poles. This generator example only has one pole, or one set of poles, where we have a positive and a negative above and below the loop, one set of flux, and then as we pass through, we get this nice waveform. But there are several factors that impact our generators. So in this case, we can increase our number of poles, but we can also increase the number of loops. So we have one coil, but as we increase loops into that coil, then we can increase, just like with an inductor and a magnetic field, we can increase the impact of the magnetic field on the induced current. A stronger field will also increase our output current, and then the speed of rotation. So how fast we move through this field will impact how fast and how high our values are, and the effect of the shape of our output waveform. So let's talk a little bit about how we describe these waveforms. So let's say we have this wave. I'm not going to draw the negative, but we've got it going up and down. Assume this is perfect. Assume my drawings aren't excellent, but assume this wave is more symmetric. And so what we have, if we look at it, if I were a better artist, is we have this repeating shape we can kind of see. And this basic shape sweeps out like this over time. And so this is what we call a cycle. Any cycle is a repeated pattern. In AC, our cycle is going to look like this. It's a sinusoidal waveform. It goes up and comes back down. It's very smooth. You can see cycles, for example, not necessarily in AC, but let's say we have a triangle waveform. Then we have it goes up, comes straight down, goes back up. These cycles can look different ways, but in general in AC, we're just going to be talking about the sinusoid. But any cycle is just something that's repeated over and over, identically. So then we talk a little bit about positive alternation and negative alternation. This is the positive alternation. We'll designate it with a P, and negative alternation. So this is just the negative and positive side of the waveform. Frequency is kind of dependent on our generator speed, but what it is how many times we get these cycles within a second. So let's say, again, this is time, this is, I don't know, we'll say it's current, which actually I should probably be designating with an I. This is I, so we have 3 cycles. Let's say, for sake of argument, this is 1 second. Then we can go through and count how many cycles we see up until this 1 second. So we got 1 cycle here, 2 cycles here, and 3. So then our frequency is how many of these happen in a second. So it's the units for frequency is hertz, but all hertz is, let me make this a little more clear. Hertz is literally just 1 over t, or in this case, the measured in 1 over seconds. So you can kind of see that. Our frequency in this case would be 3 hertz, because we have 3 happening per second. But we can actually figure out the frequency of our output. So let's say we have a generator, and we need to figure out what's the frequency of the voltage or current generated. Well, we can do that using this simple formula. So we'll walk through a pretty quick example. Generally, when you talk about this, hopefully you'll be given the number of poles in a generator. It's not too hard to determine by hand as well. Let's say I'm going to draw a loop or an example generator. Okay, so inside this, there are 2 ways to make a generator. We'll talk about that in a later module. But in this case, we're going to have, let's see, these will be, actually, we'll do this. We'll have coils on the outside, and then we'll rotate our magnets. So we've got a piece in here that's got, I'll try to draw this correctly. Okay, close enough. All right, so what we're gonna have is, let's say, north, south, north, south, north, south. So when we talk about poles, we're not talking about counting each of these. We're talking about sets of poles. So we've got 1 set of north and south here, 1 set here, 1 set here. So let's say we have a 3-pole motor in this case, or a 3-pole generator. And then we need how many rotations per minute? For sake of argument, let's say we have 7,200 RPM. Then we can figure out the frequency of our output waveform just using this formula. So I'll go ahead and write this out in a better way. We'll erase our generator and just do the calculation. So F is equal to number of poles, in this case 3 over 2. And then our RPM is 7,200 over 60. And so this 60 is really just serving us to step down from RPMs to rotations per minute to rotations per second. So then once we go through this, you can do this yourself. We get that the output frequency is going to be 180 hertz. The units are going to be 1 over seconds, so it's going to be 180 hertz. So pretty simple calculation. Doesn't matter how many poles you have. We can step this up to 6, 12, 2, 4, pretty common numbers. But we can reverse the process as well. So let's say we have an output frequency. We know how many poles, and we can figure out how quickly to spin our motor to get, or our generator, in order to get an output waveform that we like. So next, let me draw my waveform up again, even though we have a nice image one here. There we go, we got 2, we have T. We'll again call this I. It's a little lopsided. Let's see if I can draw it a little more square. So there's another value that we'll talk about, and it's really related to our frequency. All right, there we go. I, we have T. So we know there's, let's say this is 1 second, for sake of argument again. So now let's say we're interested in knowing how long one waveform takes to execute. So how long does it take us to get from 0 to skipping over this 0 to back to the end of that wave? This is our period. So period is basically just the length of the cycle in time. It's the inverse of frequency. So if we know something we have so many per second, then we can put that over 1 and we get how many seconds it takes for one cycle. So let's say we have, I don't know, 5 hertz. A waveform, in this case actually we have 2. Let's do this. Let's use what we have drawn up here. So we have 2 hertz. We have 2 waveforms that we can see in our cycle. So we can divide to get period t. We can do 1 over frequency. So we get 1/2 second. And that seems pretty intuitive, right? We've got 2. They're equally length, so they should take an equal amount of time. We got 1 second, 2 waveforms. It's 1/2 second for each one to execute. But it doesn't matter how many waveforms we have in a cycle or how many cycles we have in a second. This relationship's always the same. So one other thing that we can talk about with frequency and period and all these other ways to describe our waveform is wavelength. So this one's not going to matter as much. Wavelength's kind of somewhat dependent on speed of travel and our frequency. So we talked about, or you can think about light. So light has a bunch of different colors to it, right? We typically think of pure light as a white light, but there's red, green, blue, all these different colors. But what happens, the difference between these colors is the wavelength between them. So they all travel at the same speed of light, but they have a slightly different frequency. And so let's say this is red. I'm not exactly sure what the actual wavelengths are, but then we've got blue. And you can see that they're traveling at the same speed, but they have a different frequency, so they're going to have a different wavelength. So this might be the same amount of time, but this value is determined by how fast it moves, and it is an actual measurement in like meters or inches. Generally, it's going to be something really, really small that we can't physically measure it, but we can calculate it. But generally, when we're talking about circuits, we're not going to be worried about this because we're going to assume pretty much everything's moving speed of light, or I mean, as fast as an electron can move through our components. So this graphic here on the bottom right kind of shows a little bit about frequency, wavelength, cycle. Kind of does a little summation of all of them. We can see our 1 cycle per second, or time period, our wavelength, distance covered by 1 cycle. So one of the last things we're going to talk about in terms of our actual waveform, at least in generating it and what we'll see in circuits later, is going to be our phase. So you can imagine, again, we'll draw another graph. We've got 2 waveforms, where 1 is our voltage, and you've got it's shown here in the picture. But let's say this is our voltage, and this is, oh, not T, this is our current. Oh, I did T again. So, ignoring the small mark on the I, we've got 2 waveforms, and basically what this is saying is this: as voltage increases, current increases, and then as voltage decreases, current decreases. This is an example of in phase. The next example shown in the bottom right image is out of phase, which basically says that, you know, our voltage and current are not going up at the same time. They're not going down at the same time. And they're definitely not going up and down and reaching these maximum points at the same time. So, you know, we might redraw our current to look a little more like the one in the second picture, second image, to where it's shifted, let's say here. And so the shift will be constant. I mean, the phase shift will be such a distance here, and such a distance here, such a distance here. But we can see that we hit the maximum at 2 different points in time. So this is our out of phase, but we can talk about them as leading and lagging. And this definition we'll talk about later as well. But leading is just, it depends on which one you talk about first. But leading is the one that reaches their maximum value first. So in this particular instance, we can say voltage is leading current, I, because it reaches a maximum first. It reaches this top peak before current does. We can actually say how much it's leading if we know a little bit more about time and whatnot of our waveforms. But then additionally, we can say that the current is lagging the voltage. So this just means it reaches peak value after whatever start time. I mean, this is 0 seconds. Get rid of this mark. But basically, current is reaching its maximum value after the voltage. Now, if we were to draw I over here and we were to shift this further back, we can make I actually reach its peak value somewhere else. And then we can say that current is leading voltage, and then the voltage is lagging the current. You can say it a couple different ways. They're all correct as long as you're sure that when you say something is leading something else, the first part is the one that reaches its peak value first, and vice versa with lagging. So there are a couple other values that we're going to talk about with a waveform. These aren't frequency. These aren't really describing waveform as we will normally talk about them. These are the values that we're actually going to use the most often. So this is going to be what we're talking about with voltage or current. So let's start with just a wave. Draw another one up here. Try to make it as symmetric as possible. We can draw another cycle out here too, why not? But I didn't do a good job of showing what I want to show. So, that's close enough. All right, so there are three values that we're going to talk about. And the first one is instantaneous value. So what is this? So let's say we have voltage here, and this is time. Instantaneous value is the voltage at any point in time. So if we're to cut in here, or measure somewhere, anywhere along this waveform, could be anywhere, the instantaneous value is whatever this voltage is. If we draw it back to this axis, that is the instantaneous value. That is whatever we see at that exact moment in time. It's not a value that we'll use very often, but if you were to plug, like you have an equation for what the wave looks like, you can plug in a time and you can get out voltage. More importantly, and one that we'll see a little more often, is this peak voltage. And it's pretty intuitive. Basically, you have your maximum and minimum peaks. And this value is, I don't know, for sake of argument, 177 volts above zero. So we have 177 volts. The nice thing is these waveforms are symmetric, so we actually have negative 177 essentially down here. But this peak value is whatever the max and minimum are. So 177 is our peak voltage in this case. And we will see this every once in a while, but it's not the most common. The most common that you'll actually see is your effective value. So effective voltage, what it is let's say we have a resistor. Remember this from previous modules. Resistor, let's say it's in DC. Well, what's going to happen with a constant current is we're going to have some sort of heat dissipation. Resistor is going to dissipate potential. There's going to be heat generated. So we have some DC current. Let me draw a better arrow. We have some sort of DC current, IDC, that creates some value of heat. And so our effective voltage in AC is the same voltage that creates the same dissipation heat. So if we have an effective voltage of 120, then that effective voltage creates the same heat dissipation in a resistor as a DC 120 volt. So how do we calculate effective voltage? Well, generally it'll be given to us, but in the case that we're given peak voltage, we have a nice formula here, pretty simple. It's just a scalar between peak voltage and effective voltage, or even RMS. Sometimes you'll see V effective written as V RMS. These values are the same. I'll explain in a second what RMS is and how we calculate it. But this value, V effective, if we take from, let's say we're given peak voltage first, we can divide by 1.414. And this value, nominally, if you want to be more precise, is a let me get away from this, is root 2. So square root of 2 is equal to roughly 1.414. We won't really care where this root 2 comes from, but I'll give a hint to it when we talk about RMS. But let's say we're given our peak voltage. Let's go back to this 177. We would divide by this 1.414, and then it would give us, in this case, roughly 120. I'm not going to go into significant digits, and you know, there might be stuff behind the decimal points. But this 120 is the exact value you'd see at your home. So like 120 volts is your standard home outlet. And so what you're seeing, and when you're told that, you know, there's 120 volts in an outlet, is that is the effective voltage. That is the RMS value of your outlet. But the peak value of the voltage coming out of that outlet is this 177 volts. So anytime we're given a value, we can use this pretty simple relationship to transform between the two. You can go the opposite direction if you're given the effective voltage, then you know the peak voltage. And if you think back to when we talked about capacitors and safety rating for voltages, we talked about, you know, having a 50% overshoot. If you think about it here with capacitors, let's say you have a 50 volt DC, and that's what the capacitor is rated for, or you need 50 volts in DC. Let me erase some of this so I can make some room so we can do this calculation. If this capacitor needs to be at 50 volts effective value, or DC, it will not be good to plug it into a 50 volt effective value AC, because this 50 volts, which is VF, for our capacitor, when we multiply it by this 1.414, we see that times 50, this max value is suddenly like it's like 70, I don't know, 72 or so. 70, roughly 70, we'll say. And so this is our actual peak voltage. This is the maximum voltage that would go across the capacitor. So if you have something rated for 50 volts, suddenly it's not good enough. So that's why when we talked about capacitors, we talked about doing a 50% overshoot. That's where this comes from, this 1.41. So if you were to do 50%, it's like multiplying it by 1.5. So then you've suddenly got this cushion of about 5 volts. It's not great. You would ideally have actually a larger cushion than that, but it's better than plugging a capacitor into a circuit it's not rated for. So a little bit more about effective voltage, why this 1.41 exists, mathematically how we get this DC value out of an AC circuit. Well, you can think of this waveform as this. So it goes positive, it goes negative, you have change in current. But DC, you know, is going to have, let's say down here, we have just this constant voltage. It's a little hard to see. I'll darken that up a little bit. So we have a more constant waveform down here. But the one thing you can also notice, if this is 0 for volts, all of these, this value is always positive. It's always flowing in a positive direction, but the AC waveform is not. So the easiest way to get from positive and negative to purely positive is we square it. So we take this waveform, we square it, all the values get squared. They're made a little bit larger, so this peak value is suddenly a lot larger than it originally was. But what we can do is we take the average of it, roughly, that's probably roughly the average of this waveform. So suddenly now we have this nice flat line, but we have to remember that we squared something before, so now we need to take the square root again. And so suddenly we get this nice flat DC line that's just this, or it's the same value as the one we see here. So that's what RMS means. That's how we get this effective value, how it's easy to calculate. But the nice thing is it's summarized by this equation. So suddenly we don't have to worry about squaring it and taking the average and taking the square root again. we can just divide or multiply by the 1.1414, depending on which direction we're going. But generally, when you're given a problem in AC, unless it says outright that it's a peak voltage, generally you can assume you're seeing RMS. It's the same when you're looking at machinery, anything in the field. Most likely they will give you the effective value of an AC waveform, a generator, and what you have to be careful of is when you're trying to decide, okay, what capacitor do I put on this circuit? You have to keep in mind what that peak value is going to be of your waveform. You can't just see 120 is coming out of the outlet and say, oh, I can just get a capacitor that's rated for even 130, because once you multiply by this 1.41, it's suddenly way over the max value for the capacitor. So in summary today, we've talked about AC. We talked about how it's always changing direction, magnitude, but it is good for aircraft. You'll see it's great for transmission, saving space, safer at high altitudes. We talked about how we create AC with generators, inducing current through a magnetic field. We talked about the left-hand rule for generators as opposed to the left-hand rule for EMF. This is very important when you're talking about generators. We talked about how to get frequency out of a generator given number of poles, rotation per minute. And then we just talked about how to describe waveforms. So we've talked about frequency, wavelength, cycles, period. We talked about phases. And then we've also talked about max and min values, peak values, and our effective value for voltage, current, and everything else.